When we introduced the first law, we indicated that as a result of work and heat exchange between the system and the surroundings, that is the process, the energy of the system changed, say from some initial value, U sub I, to some final value, U sub F. The first law relates the change in the system's energy between the initial and the final states of the system to the work and the heat. So we can visualize a process as changing the state of a cylindrical object. For instance, from an initial state characterized by a small size and by a blue color for cold, to a final state characterized by a larger size and an orange color for warm. The process involves some work, W1, since there is a change in the volume of the system. The process also involves some heat, Q1, since there is a change in the temperature of the system. The experiment we have just described is the heating of some cylindrical object. Now we can envision different ways of heating this object, for instance, using different heating rates or different methods of heating, trying to initially keep the diameter of the object constant or trying to keep its length constant, and vice versa. So in essence, we can imagine that we carry out the process of heating using different paths. In the second path considered, the work will be W2 and the heat will be Q2. Because the path followed is different, the work and the heat will be different along the different path. Similarly, following a third path, the work will be W3 and the heat will be Q3. All paths have the same initial state and all paths have the same final state. So the change in energy, delta U, for all paths is the same. It is equal to the difference UF minus UI, the energy in the final state minus the energy in the initial state. We can write that delta U equals UF minus UI equals W1 plus Q1 for the first path equals W2 plus Q2 for the second path equals W3 plus Q3 for the third path. We say that the change in energy U is independent of the path chosen, while the work and the heat do depend on the path. This argument made with the energy U can be made with the system's volume, since the change in the system's volume is the same through the three paths. We said that properties like energy, pressure, volume, temperature, entropy, S, and enthalpy, H, and Gibbs free energy, G, are state functions, since they are completely defined for any given equilibrium state of the system. Any change delta x in a state function x between an initial state I and a final state f is simply the difference x sub f minus x sub I, where x sub f is the value of the function x in the final state f and x sub I is the value of the function x in the initial state I. Work W and heat Q, however, are functions that cannot be defined for a particular state of the system. These functions are only defined during a process between some initial and some final state. The magnitudes of the work W1, W2, W3 are generally different from one another. The same can be said about the magnitudes Q1, Q2 and Q3 for the heat in path 1, 2 and 3. In contrast to delta U, delta V, delta T and so on, the magnitude of the work, or that of the heat, depends on the path taken between initial and final state. This is why we call work and heat path functions. To illustrate the concepts of state and path functions, let us consider the adiabatic compression of an ideal gas between states I and F. The process is adiabatic, so the heat is equal to Q is equal to 0. Remember that I'm using green boundaries to characterize systems which exhibit an adiabatic boundary with the surroundings. Since we are dealing with compressions, Vf, the final value of the system, is going to be smaller than Vi, the initial volume of the system. Therefore, work must be done on the system for the volume to decrease. The work is therefore positive. Using the first law, delta U equals W plus Q, we conclude that the change in energy for this process is positive. So the energy of the final state of the system is greater than the energy of the initial state of the system. Since the gas is assumed to behave ideally, the gas energy only depends on temperature. So we conclude that the final temperature of the system must be greater than the initial temperature of the system. This is a very general result for adiabatic compressions of ideal gases. Temperature increases during the compression and decreases during expansion. Let us now carry the transformation of the system from state I to state F using a different path, going through an intermediate equilibrium state which we will call state X. The state X is chosen so it exhibits the same temperature as the initial state I and the same volume as the final state F. The first stage of this new path is therefore an isothermal compression, since Tx equals Ti and Vx, which is the same as Vf, is less than Vi. And the change in energy for this process is equal to delta U prime equals Ux minus Ui. The second stage of the second path is an isochoric heating from state X to state F. It is isochoric because Vx equals Vf. It is a heating process because Tf is greater than Tx, which was chosen to be equal to Ti. The change in energy between initial and final states can therefore be written delta U equals Uf minus Ui. If we add and subtract U sub x to these terms, which is like adding 0, we can rewrite delta U as Uf minus Ux plus Ux minus Ui. So in conclusion, we can see that delta U is equal to the sum of delta U prime plus delta U double prime. The change in energy is therefore independent of the path. The previous two processes can be more clearly represented using a schematic of temperature as a function of volume. The first path discussed on the previous slide is shown by the following curve, marked as adiabatic between the initial and final states. The second path discussed on the previous slide is a sequence of two steps. The first one is an isothermal process at the initial temperature T sub I from volume Vi to volume V sub x equals V sub f. The second step is in isochoric heating at constant volume Vx equals Vf from temperature Tx equal to Ti to the final temperature T sub f. Note that we could have accomplished this change from state I to state F using another two-stage process through a state Y, where the first step is an isochoric heating at Vi equals Vy from temperature Ti to temperature Tf, and the second step is an isothermal compression from state Y to state F. We will see in this chapter, and especially in the next chapter dealing with entropy, that such graphical procedures are very useful for the calculation of changes in properties of a system in terms of changes in properties resulting from simple isothermal, isobaric, or isochoric processes.